Congratulations for making it to the final section of this course, which looks at the design and operation of transformers. Transformers are an essential part of the network and allow it to operate efficiently and safely. By the end of this section, you will understand why we need them and how they operate. The aims of the course today are to show what a transformer is and how it operates, to introduce the basic transformer equations, to show how a transformer can be used in specialized situations, here we have a standard coil. Here we have a coil fed from an AC source and controlled by a switch. When we close the switch, current flows through the coil and the coil becomes magnetized with an alternating magnetic field. Now let's see what happens when we bring another coil into its magnetic field. A voltage will be induced onto coil B as the lines of alternating magnetism are cut. If a circuit is now connected to coil B, a current will flow in it, and electrical energy will be transferred from coil A to coil B. This arrangement is called a transformer. So here we have a transformer with winding A and winding B. Winding A has voltage A and current A. Winding B has voltage B and current B. Note that the current in winding B is in the opposite direction to the one in winding A. If we want to improve the magnetic link between the windings, we can add an iron ring that passes through them both to form a continuous magnetic path. This is called a magnetic core. We call the number of times the wires are looped around the core the number of turns. So for the above example, both windings A and B have 15 turns each. Let's look at some of the characteristics of a transformer. If windings A and B have the same number of turns, winding A voltage VA equals winding B voltage VB. Winding A current IA equals winding B current IB. Winding A power in equals winding B power out. If we now make it so that winding B has half the turns of winding A, then winding A voltage VA equals twice winding B voltage VB. Winding A current IA is now half winding B current IB. Because the power is the summation of the voltage and the current, winding A power in still equals winding B power out. Therefore, we have changed the output voltage and current by changing the number of turns on each winding. Even though the ratio of the input and output voltages and currents has changed, the power flow through the transformer has stayed the same. By knowing the precise number of turns in each winding, we can work out the transformer turns ratio, which establishes the ratio of the currents and voltages. Transformer turns ratio equals the number of turns on winding A divided by the number of turns on winding B, equals NA divided by NB. The voltage ratio equals the voltage on winding A divided by the voltage on winding B, equals the transformer turns ratio NA over NB. The current ratio equals the current in winding A divided by the current in winding B, equals the inverse of the transformer turns ratio, NB over NA. Let's do a worked example. For the transformer shown, what is the value of VB and IB? From the previous slide, transformer turns ratio equals NA over NB. From above, this equals 1000, which is NA, divided by 10, which is NB. This equals 100. Therefore, VA over VB equals the transformer turns ratio equals 100. Therefore, VB equals 230, which is the voltage on winding A, divided by the turns ratio, which is 100. Therefore, VB equals 2.3 volts. The current ratio is the inverse of this, so therefore the current ratio equals NB over NA, equals 10 divided by 1000, equals 0.01. Therefore, IA over IB equals 0.01. IB equals 10, which is the current on winding A, divided by 0.01. Therefore, IB equals 1000 amps. We can see from the above that the voltage on winding B is now 1/100th of the voltage on winding A. The current on winding B is 100 times the current on winding A. But remember, the power will remain the same on both windings. The power rating of the transformer is the maximum amount of energy that can continuously pass from winding A to winding B, or vice versa. Here we have the transformer from before. Here we have VA max, which is the maximum rated voltage for winding A, and IA max, which is the maximum rated current for winding A. On winding B, we have VB max, which is the maximum rated voltage for winding B, and IB max, which is the maximum rated current for winding B. The transformer power rating equals the maximum rated voltage on winding A multiplied by the maximum rated current on winding A, or the maximum rated voltage on winding B multiplied by the maximum rated current on winding B. The transformer power rating is measured in VAs. Note that for the transformer rating, we do not consider any power factor. When we are dealing with transformers, we usually call winding A the source winding, the primary winding, and winding B the load winding, the secondary winding. So here we have the transformer from before. On the primary winding, we have the primary current IP and primary voltage Vp. On the secondary winding, we have the secondary current Is and secondary voltage Vs. We have to be very careful with transformers, as very large currents and voltages can be created. For example, imagine a transformer with 1 turn on the primary and 10,000 turns on the secondary. This would result in the voltage on the secondary winding terminals being 10,000 times higher than the primary input voltage, which could be very hazardous. Let's look at one way we can use this high ratio effect to good use. If we place a high turns winding around a conductor carrying current, the electric field of that conductor would induce a small representative current in the winding. This device is called a current transformer, or CT, and is used for measuring purposes. The value of the current ICT will depend on the number of turns on the current transformer. With ICT equaling the current flowing through the conductor divided by the number of turns on the CT. Let's do a worked example. Calculate the value of the secondary current ICT. From the previous slide, ICT equals the current flowing through the conductor divided by the turns ratio. From above, this equals 1600 amps divided by 900 equals 1.77 amps. The CT current is a direct representation of the main conductor current. CTs are used widely in electrical systems to monitor the main currents, ensuring that the system is healthy. Let's summarise what we've learned today. If two windings are brought close together and one is energised with AC, then a voltage will be induced from one to the other. If we connect a circuit, current will flow in the second winding and power will be transferred from the first winding to the next. This arrangement is called a transformer. We can alter the value of the voltages and currents that are induced in the second winding by altering the turns ratio. We call the source winding the primary winding and the load winding the secondary winding. We can create a current transformer that can accurately measure the current in a conductor. Well done for completing the electrical power equipment course. I hope you now understand all of the basic elements of the power networks and why they look the way they do. Now that you understand all of the basic power elements, future modules will start going into more detail to get you to an advanced stage of learning. The next section will start this theme by covering in detail protection system design. I hope to see you then.